กันนะครับเนื้อหาในวันนี้นะฮะก็เรามาต่อกันนะครับก็ทุกคนคงยังทำ assignment อยู่เนาะที่ในการ implement ตัว stochastic นะครับ gradient descent ตัวนั้นนะครับก็สำหรับวันนี้นะจะเป็นการที่มาดูในเชิงของทฤษฎีนะครับเราจะมาดูถึงคอนเซปต์นะว่าเวลาที่เราพูดถึงmachine learning เนี่ยนะครับในในการที่มันไปเรียนรู้เนี่ยนะครับมันไปเรียนรู้พารามิเตอร์อะไรนะเราจะไปดูคอนเซปต์ต่างๆใน Machine Learning นะครับตั้งแต่การที่เราฟิตใน Data เนี่ยมันเกิดอะไรขึ้นนะครับการที่เราใส่ตัว regularization นะใส่ตัวพารามิเตอร์ที่จะช่วยทำให้โมเดลมันมีความเรียกว่าเราสามารถที่จะใช้ได้โดยที่มันไม่ได้ฟิตไปกับ Data ชุดหนึ่งๆนะที่มันดูแพทเทิร์นมานะครับมันจะต้องมีแนวคิดอย่างไรนะครับเราจะมาดูในวันนี้นะฮะก็จะมาดูคอนเซปต์ของ Machine Learning นะครับก็เริ่มกันเลยนะครับเวลาที่เราดูถึง Machine Learning เนี่ยนะครับเราอาจจะเคยได้ยินว่ามันมีอัลกอริทึมหลายๆตัวนะที่เกี่ยวข้องกับ Machine Learning นะครับมี Decision Tree มี Random Forest Logistic Regression นะฮะหลายๆอันตรงนั้นมันก็มาจากเทคนิคทางด้านสถิตินะครับที่ถูกนำมาประยุกต์นะครับเพื่อที่จะให้มันทำงานได้ดีขึ้นนะครับเพื่อที่จะให้มันสามารถไปจำแพทเทิร์นนะครับแล้วก็เรียนรู้นำออกมาใช้ได้นะครับในงานต่างๆนะครับดังนั้นนะครับเวลาเรามาดูวิชาของเราเนี่ยวิชา Deep Learning เนี่ยมันก็เป็นส่วนหนึ่งนะครับของ Machine Learning นะครับรูปทางขวานะครับแสดงให้เห็นถึงว่า Deep Learning นะครับอ๋อลืม สอนภาษาไทยหลายรอบไปหน่อยลืมเลยเอาใหม่เดี๋ยวเทค ต้องไปอัดวิดีโอด้วยโอเคนะเขินเลย I totally forgot that this is English class right and yeah and just realized that something's weird I kind of have been going on for a bit there um, yeah so my apology on that uh, yeah anyway let's get started on today's topic. The topic is machine learning, right? We will learn the basic concepts and the formulation of machine learning on the different I'll say on the mathematical base rather than on the coding part. Okay. Machine learning is part of different applications. We have seen that we have been seeing that have been adopting in today business, in today applications. What we have, and when we talk about the specialized part of machine learning that deal with the unstructured data, that deal with the representation, try to learn representation from the data. We are talking about deep learning, and this is the focus of this course. Deep learning is part of machine learning. If you look on the right-hand side, you will see that when we talk about deep learning, it is actually a subset of the whole machine learning things. There are other techniques in machine learning like decision tree, logistic regression, or random forest, boosting, backing. Those are the techniques that allow you to learn patterns from data. Deep learning as well. The aim is to learn patterns from data to generalize from the pairing between input and output and let the model trying to find the way to connect the pattern, the input pattern to the output patterns. So if we were to talk back maybe 20 years ago, neural network or the deep learning technique have been thought of as the way that you can perform functional modeling, that you can create the representation of the function, let the model learn the representation, the association between input and output, and identify important mapping between them in such a way that you could utilize that function again because you have let it learn from the data. You can utilize that again to perform the task next time. That is actually the technique of the concept of generalization, that you would want the model to be able, or actually it doesn't have to be the model. You would want the theory, the thing that you want to explain the world, aka the model, to be able to apply to different tasks, right? And one of that is to capture the mapping between input and output, like I said earlier. Uh, in order to understand deep learning, though, we need to talk about the bigger topics, bigger concept of machine learning. Okay, let's move on. Right. When we talk, what is machine learning? Machine learning has been defined on a different perspective, on a different level. On the one hand, you can define machine learning as the pattern modeler, as the function that could capture pattern and then can be used to perform different tasks, right? But that would be on the coding level, right? But we will talk about more of the basic level. How do we explain machine learning? Right? What is it? We can say that machine learning is a program, right? It is a program that learn from certain experience. And for supervised learning, it will learn from the input and output observations. For the unsupervised learning, machine learning will learn from the similarity of the patterns. In the semi-supervised, it might kind of doing something hybrid between the two. Or in the reinforcement learning, the machine learning has to reinforce the rule, reinforce from environment, and then keep iteratively learn patterns, learn the behavior, learn the concepts from environment. So we can say that the program, the machine learning program, has to learn from certain experience E that we define here, and this experience E, or the observation, aka the observations experience, has to be experience of some type of task, which will differ depending on what we are talking about, right? If we talk about doing something like sentiment analysis, then the task would be to predict the sentiment, and the experience would be the text that you need to, that say if we talk about human doing the prediction, that person has to read through the data and then trying to judge whether that text is positive or negative, right? In machine learning, in the program here, we want the program to learn from experience, to learn from what it has observed, and then perform certain tasks. Right. So it can be different tasks, it can be different things. So this is just a way to generalize it, and we would have certain performance measurements. Like for classification, we talk about predicting the right category. Then that would be the accuracy. If we talk about having the best trade-off between precision and recall, then we will talk about F1 score. Right? And those are the metrics. Those are the performance measurements. Different tasks would have different performance measurements. So if it perform in the task T and measured by P and improved by experience E, that would mean that if we provide more data, right, the program should learn these patterns and be better by the performance measurement P, right, and with the certain experience E. This is one of the definition of machine learning. Now let's look at different scenario that we can define P, T, and E. Okay, I will point out some of these P, T, and E, and I want you to think on different, I would say, applications of machine learning now today, and think about them in terms of this P, T, and E, and what are they in different applications, and maybe later on I want your input on those. Just think about some examples and then give me later on. Okay, so let's first look at different definition of the task, the experience, and the performance measure. First, the task. In the classification, if the task is to predict the class, or we call that classification task. The classification task, the program is asked to identify the category. Given the category, right, the program has to provide the class. So, well, let me sign in first here. deep learning. Okay, so for this task, right, what it need to perform is to after receiving X, it need to produce Y. Y here has to be in the category of 1 to K. It has to produce the index value of the class that the input belong to. Like in the sentiment analysis, we might have two classes. That means for 0, we could think of that as negative sentiment. For 1, that would be positive sentiment. And the model need to learn how to predict one out of the rest. Right? For topic prediction, if we want the model to estimate whether the document should belong to which category, right? Whether the news should belong to politics, sport, finance, by reading through the news, and it has to learn the patterns. In that case, X would be documents and Y would be the class, right? So that's classification. Okay, the next task is regression. In regression model, this would be different from earlier. Right? In regression, it would be the mapping between from Rn to domain of R, the real value. That means the task is to estimate the value from input. That means from the input, it has to crunch down, regress to a single value that you could use that in estimation, maybe of the activities of the using it to do the demand forecast, that type of things for regression tasks. Task T can be unsupervised as well. It can be clustering. In clustering, the program needs to divide the data into groups. So if you think about it as input and output, it also try to map Rn, try to map each instance of input into a cluster, right? A class, a label. But instead of letting it learn from the pairing between input and output earlier, it needs to learn by itself in order to separate the data into, let's say, K classes. Yeah, like the task that if we were to perform customer segmentation, separate the customer into groups based on the behavior of the customer in purchasing products. We can create the variables of recencies since when the customer has not come to the shop, frequency, the frequency of purchase in the past, say, 3 months, monetary the amount that the customer purchased in the last 3 months, for example. Okay, this is also the task. The task can be more cognitive, like transcription task. In a transcription task, the program has to learn the unstructured, the association between unstructured representation and the text underlying those unstructured representation. Right? So it means that it has to receive the voice and then transcribe it into text. And then from the text, we can use this text to perform different tasks. Like in a mobile phone, you can using the keyboard to type the text that you want to talk instead of typing it yourself. Okay, in order to do so, we need to have a model to train the system called speech recognition system. Earlier, before the era of deep learning, this system is learned through a machine learning model like the Markov models. But in the, I would say, in the current de facto speech recognizers, it is actually the hybrid model between the traditional state-based model like the Markov model and the more advanced deep learning like the recurrent neural network. and the and author modification from that. Okay, so the task of transcription is to transcribe, is to map each voice, each phoneme, like you have the speech looks like this. In transcription, right, the aim is to map from this data into the class. This can be, say, deep learning, like that. Okay, this is the transcription task. In machine translation, right, the input and output would both be sequence of character. Now, they would both be sequence of words, depending on the languages we talk about. So in machine translation in the MT, the source text need to be translated into the target text. Usually the idea is of translation can be done through certain direct mapping, direct translation, or it can be done through a certain medium. This is the old concept of machine translation, that if we could map from the text of a specific language into the kind of universal representation, and then we can create a generation system that generates it out. And in the, I would say, the latest revision of these concepts in deep learning has led to the encoder and decoder style model, and it worked quite well. And then also the transformer model that has been applied to perform the machine translation task. Okay, so the task of machine translation is to translate from text to text, but it needs certain mapping, certain generation and decoding of the source text and generation of the target text. The task of anomaly detection. Input of such tasks would be certain signals. So the program has to go through different types of objects. It can be the signal object, it can be image, and if you are video or the data in the file, in order to identify the fraudulent or the problems in the data. This is the concepts of anomaly detection. You can see that the task T has to receive a bunch of input and then alert when there is an anomaly. Right? So this is the behavior of this task. Task T can be performing synthesis. This is difficult comparing to the earlier mentioning. Synthesis and sampling is the task that I would say has arisen in just the recent years, that you can train the deep learning model to replace faces onto the image, onto the video. You can use it to render the live video, right, to have like different texture. It's quite great. It's quite fascinating that we have those type of technique that allow you to do such that. Okay, so this is a picture from the defect that you can kind of let the system learn from a bunch of data, and then it learn to generate, to replace the input data onto the original file, or learn to generate the data out. So these are a set of tasks that are available in that I can think of, put it this way. Now, what I want you to think and then give me some examples are the application that you have seen in real life that utilizing these tasks. So just give me the task itself and mentioning about the type of task it is, and also input that the program receive, the output that it produce, right? Think about some examples and type away. I put it into the chat, and then I will read for our friends in the class here. Right, help me here. Give me some examples. I need 5 to go on. I need at least 5 examples to refill and then go on to the next topic. Application, type of task, input, output. This could be things that related to simple machine learning. It doesn't have to be deep learning though. Just think about them. That the application that you have seen, you might use already in today's life, in the daily life. Think about them and then give me examples here. Still waiting. As I said, I need 5 examples to go on from this point. Google Translate. Do the machine translation, input text to output text. Okay. Acceptable, I guess. Although it's repeat what I said, but fine. Next. Okay, 20% refill. Ready to go. Come on. What else could it be? Look around you. Look around you. Do you see any things around you that use machine learning? Think about since the morning. Have you used systems that use machine learning? If so, yeah, I'd like to know the types of tasks that it performs and input and output, or just input if it has only input, or just output if it has only output that algorithm, that task utilized. Well, Apple Watch do anomaly detection, error movement such as fall down, and doing it. Yeah, that would do as well. It detect the movement. And then interpret whether that movement is an emergency or not, and give the SOS, give the alert if that's the case. Okay, Natawat has already gave me twice already the output. How about the others? Yeah, Face ID, right. Yeah, just look at your mobile phone. It has now used Face ID to lock your phone, it perform classification, or I would say that is actually the verification. It's the classification, but it is actually, well, binary classification is the verification, and it received the input picture. Okay. Or actually it might detect the telemetry rather than picture, and the output maybe the class. It actually verify that you are the owner of the phone or not. Verification is the same as classification, but it's 0 and 1. But that's all right. Google Voice Keyboard transcription task, input voice, text output. Yeah, image search from Google, and image recognition, input image, output search result. Okay, right. And the search result would be the set of documents that close to, or the set of picture that are similar to that picture, right, for the Google image search. Okay, good. let's move on. I lost count. Should be enough. Okay, those are the T. Now I want you to keep looking. This T will change, right? This T will be increased. And once you see those T increase, that will be like an entirely field for research, because the tasks that I mentioned here are not new at all. These are the tasks that have been here for, I would say, 40 years, 50 years. Earlier, these were done by rule-based methods, and then by the computerized rule-based, then by machine learning, and now today by deep learning. Okay. For some of them, though, right? Some of what I mentioned, like anomaly or some tasks, using machine learning is still fine. You don't need to have complicated method to solve simple tasks. Okay, next is the performance, right? Once we have the task, we need to have a way to measure performance of different tasks. For classification, the way to measure the performance of the classification can be done different ways. One of that is to measure the area under the ROC curve, the receiver operating characteristic curve. This curve will tell you the trade-off between the true positive rate and false positive rate, basically. So if the value here is close to 1, then you know that it is quite good. But this can be only applied to binary classification. If the task that you are working on is not binary classification, then you better look at the confusion metrics to see how well the model predict the class. And then from those, you can calculate different types of metrics like precision recall and accuracy. For multi-class classification, accuracy might be a good idea if you have balanced class. Otherwise, you might need to think of the strategy that would allow you to assess the performance of the model. Like you might doing something that is called one against the rest. That is, suppose that you have say 4 class, A, B, C, A, B, C, D to predict. You might do this, right? You might try to evaluate the model rather than evaluating everything at the same time as accuracy. And if it predict correctly, count as 1. If not, count as 0. That's okay if they are balanced, right? If these are balanced, then that should be fine. But in reality, we often find that A, B, C, D, these class labels are often skewed, that some class dominate the other class. And in that sense, if these were to be evaluated as accuracy, it wouldn't be fair, because the majority class would always rule. The majority class would always got the vote because it got like would always has the better accuracy than the rest, because the model would kind of gear toward that model. So instead of doing that, there is a strategy called one against the rest. This technique, we can perform evaluation of class in a bunch like this. So we measure the performance of detecting certain class comparing to the other class. And in each case, this will be thought of as having label 1, and this will be thought of having label 0. And then we can use the same technique that we can perform in binary classification, like using the area under the curve, ROC curve, evaluating precision and recall to determine the model performance of each class label. Okay. In case you might have not known, the precision and recall the measurement that measure how precise the model is. Like for the precision, suppose that we have two positive sample is on the left-hand side, the relevant element, and negative sample is on the right-hand side. Precision is precision is the I would say how accurate the positive prediction is. I suppose that so the positive prediction is the circle here. Right? Suppose that we predict all of these instances as positive. The precision is the proportion between the left hemisphere here dividing by the whole circle. So and that would allow you to determine how precise the model is. So if the model is precise, then it will rarely predict wrong instance. That's precise model, but it's just like us human, that if in some case, if we were not sure whether we are correct, we might stay silent, but we might miss the chance. So if we were to talk too much, then we will kind of maybe ruin the chance as well. We will not be accurate. So that this is like the similar analogy with that. For the recall, it is the proportion that the model can filter relevant element out of the whole things. So if we were to select a certain threshold that the model has to predict yes, like at 50% or at 60% or at the 30%, and then we were to measure and if we were to treat the probability that is beyond that probability as positive, then we can count the number of instances that were classified as correct, right? That we can detect of, and then divide them by the total number of relevant elements, and there you got the recall. That's a proportion that you can filter from the population. Okay, so this is for classification. For regression, there are different matrices depending on the distribution of the data. If the data are normally distributed, you can use R square, right? And you can also measure the error using the MAE, mean absolute error, or the RMST, the root mean square error. But these are just two of a lot of metrics that I gave here. But there are other measurements for different machine learning tasks. Like if we talk about transcription, then you can measure the word error rate to determine whether transcription is good or not. If we talk about the language model generating the text, there are the perplexity that can be measured. So there will be different types of measurement depending on the task that we talk about there. In performance evaluation, we need to we also need to separate the data so that the performance would not be biased or to the data set. Right. So and one way to do that is to perform the technique called hold out. Hold out is to hold the data, part of the data to train, and use another part to test. So this training set can then be further evaluated by using technique like cross-validation to identify the best parameters, the best model out of the training set, and then test it with the tested. Okay, so this is for the performance. And for the experience in terms of the, sorry, and this is actually the experience that I'm talking about. I forgot to delete this slide. The experience, the data that we need to collect of that task, right? Need to separate them into two. But in some case, you might not need to. Right? For example, if the task is to identify the group and to do the clustering, we might not need to do the validation like this, because the end result is to separate the data into group, not perform prediction. Right? So it depends on the task. Right? The experience would be different as well. And this would lead to the different types of data accumulation and data preparations. The success of the project sometimes depending on having the right data set. If the data set is not suitable for applying to a certain task, then you will not be able to perform the task. For example, if you want to perform time series prediction, time series forecast using LSTM, right? You need to have the data set that contains terms, otherwise you would not be able to do so. Right? So that's it. You need to have the data in the proper format that to be used with the task. And then in performance evaluation of the training set, we can perform the cross validation to reduce the chance that the model would overfit to that data set by separating the data into chunk, and then use one to test to validate, and the rest for training, and then repeat this k time. Then we can average the performance altogether later on. Okay, so yeah, so these are different types of the T, P, and E. Okay, now we are going to just look at one simple example and then look at P, T, and E on how to define and then learn parameters based on these notations. Let's look at a very simple example here, the linear regression problem. In the linear regression problem, the goal of this is to take in the input vector x, which is real vector, right? And then predict the scalar value y. Okay, we take input vector x, predict y. Output of the linear regression that we need to learn will be the linear function. Okay, and for that we can write the model that we use x to predict y as in this equation. That is, here is y, and then we have x as the real input, and this x is dot. This transpose multiplication is actually a dot product between the weight vector and x. So I can write it this way as well. This y hat is actually the dot of w and x, right? And because here we know that this is w1, w2 to wk, and this will be x1, x2 to xk. So this would be w1 x1 plus w2 x2 plus wk xk. Right? This is the dot product. But rather than writing it this way, it can be written as the matrix multiplication with transposition. Because if you were to transpose it, think about w as the row vector, and then x is a column vector. When row vector collide with column vector, you get the dot product. Okay. So this is the task. The task is to compute y by multiplying w and x, w transpose and x. Okay. Predict y from x. So from this task, the unknown that need to be learned is the vector w, right? And the values in the vector w. These are the values that need to be learned from the existing data of x and y. Okay. Now we know the first item, the task, which is a regression task. Next is the measurement, the performance measurement. Or sometimes this is called the objective function, the cost function, the error function. In this case, we will deal with it in a way, in the linear fashion. Right? This is the mean square error function. Mean square error function measure the difference between the prediction with the actual prediction of y with the actual y, right? And then square, and then sum for every instance, sum them all for every instance, and divided by the number of points. Okay, so this is the mean of the square error. All right. So what I'm going to show you next is the similar notation, but I'm going to work on it in the non-vector calculus way. Then we can take a look at the vector calculus way on the next page later on. Okay, let me share you this screen. All right. Okay. So what we are talking about is y hat equal, what should I write here? Y hat is actually the summation of I equal, let's use 0. Oops. Let's use 1 then. And equal 1 to, for this one, let's use k, because we are going to use n as the number of point of wi xi. Right, this is another way to write it in the, I would say, the scalar form, the summation form. And then for the error function, this is the 1 over m summation of, let's use j then, j equal 1 to m of the prediction y j hat minus yj square. Okay, then I'm going to replace yj hat with the y here. Sorry, I've used I here. No, this is I. I have made mistake here. Okay, because you probably have multiple data points, right, and to estimate here, like that. So what I'm going to do here is to replace the summation of j equal 1 to m, replace yj hat with the summation of I equal 1 to k of wi, and this one would be x. What should I do here? Xji, right? This row column, and then minus yj square. Yeah, like that. So next, because what I want to know, and this is linear function, what I want to know is to find the value of w, right? To derive for the value of w. So do is ke by ke wi, this equal, then this would be the partial derivative, because we are talking about w, multiple w's. So for example, if we talk about like just a simple linear regression, then we will have two w1 and w2, one for an instance for the constant value, and another one for the value of x itself. Right? So for this one, well, this would be 1 over m, and I should draw the 2 down here first, 2 over m, and summation of j equal 1 to m, summation of I equal 1 to k of wi, xji minus yj. By pulling 2 down and then take derivative of the inside. From the look, you can see that there is only one term that contain w. I think I need to delete this. Can I specify the size? No. Let me draw j. No. X, J, and I. Okay, there is only one term that contains Yeah, I think I'm gonna use this. That contain W, which is this term. Right? It contains W. So yeah, what I'm going to do here is to, because I have to take derivative of the inside and only Wi xji contains this um, W value, W coefficients. So the remaining here would be xji. We need to treat it as constant when we are doing the partial derivative of the terms. And that applies for yj as well. Treat it as constant, so partial derivative, that would be 0. Right, so now we have this term, the partial derivative. And as you can see that the partial derivative here, depending on the difference between output and the input, right? If we want to know, in this case, since it is just a linear regression, we want to know the lowest value, then we need to set the partial derivative to 0, right? Set the partial derivative to 0. That make and that would also eliminate, because we can multiply 2 over m over 2, and yeah, never mind. Just write it down first. J equal 1 to m summation of I equal 1 to k wi xji minus yj xji. And then I'm going to remove the first part here and multiply this inside the equation. So yeah, what I would have here is summation of j equal 1 to m of sigma I equal 1 to k of w I xji square minus xji and yj. Okay, so it's just a combination of for now we have the combination that you can see that the two here are different terms. That means I can separate them. So for this one, it's summation of j equal 1 to m sigma I equal 1 to k of wi xji square, and then minus, and then minus summation of j, no, forget about it. Okay, because there's this as well. I forgot to look at that. Usually I would just use a simple linear regression of two terms, but I forgot to replace this first. Once you multiply it in, then both you cannot multiply it in because there's, yeah. Now let me retrace it a bit. Because there is I here, and that means this is a summation of the whole thing. Yeah. I actually made a mistake here.
John, I want to ask how to over M goes.
Wait a second, there's actually more serious problem than that.
Okay.
The more serious problem is that I forgot the parentheses, and that is not okay here, because this, you see, well, I should make it simpler than this though. You see here, because this xij this xij is actually contain the element of I here as well. Right. So once you multiply it, you have the I here and the same as the I outside here. So multiply xji in, that would mean only particular j that are outside, not the whole j. It's not xji square. Yeah, sorry, I think this is a mess up examples. I think we need to use a better, simpler one. Yeah, let do it again in a simpler term. Right. So instead of doing that, I will just give you a simpler one that like y equal w1 plus w2 w1 x1 actually plus w2, but let's say x1 is 0, x2 like this. So we have y equal w1 and x1 is 0, and then w2 x2. And we want to learn w1 and w2. Actually, this is the same things as I used the notation there, but instead of using the whole equations, let's use a simpler terms like this, and that will make this E equal the summation 1 over m I from 1 to m of the yi hat minus yi square. And this is actually I equal 1 to m of yi is w1 plus w2 and then xi2 minus yi square. Right, put it this way is simpler because it contains only three parts, and then you can see it solved in using the systems of linear equation as well. Otherwise, if I were to use that full form, that would be difficult to show the least square method like this. Right. So once we expand the term, let's take derivative, partial derivative here. It's curl E by curl W1. Let's take one at a time. Curl E by curl W1 is 1 over m, 2 over m, right? And the summation of I equal 1 to m of just W1. The inside is the same because we pull 2 down, the parentheses still stay the same, yi. But we need to take derivative of the inside. This is just W1, and that make this is 1, okay? And from this, we can arrange the term 2 over m, and then we would have this as summation of I equal 1 to m of W1 plus summation of I equal 1 to m of W2 xi2, right? And then minus summation of I equal 1 to m of yi. Then we can set this to 0, right? Once you set this to 0, well, you ask me, right, where is this go? It's gone because you can simply multiply m over 2 on both sides, right? Once you multiply m over 2 on both sides, it's just simply canceling the constant value. Right. So then I'm going to arrange the side of the equation so that we have the one that contains x and the one that contains unknowns on left hand side, and the one that contains known value on the right hand side. What are the unknowns? This one and this one. Right. Before doing that, I'm going to rewrite it a bit for simple understanding, right? This would be, this is, the first term is W1 M time. So this is MW1. And the second one is, because W2 is a constant here, it's just one value. So this would be plus summation of I equal 1 to M of xi2 multiplied by W2. You can pull W2 out, right? Because W2 contains in every terms here. So you can just pull it out and then rearrange it this way. And minus summation of I equal 1 to M of yi. Right now, I'm going to rearrange so that the unknown will be on the left-hand side and the known value will be on the right-hand side. And for this one, we got this MW1 plus summation of I equal 1 to M xi2 of W2 equal summation of I equal 1 to M of yi. This would be the first equation. Now we got the first equation. Let's consider the second one, the W2. For W2, the curl E by curl W2 equal 2 over M summation of I equal 1 to M of W1 plus W2 xi2 minus yi. And then the second term would need to be the terms that contains, would need to be the partial derivative of the term that contains W2, because that would be the only term remaining. And we know from the look here that only this term contains W2. That make the remaining here the xi2, right? And then do the same thing to simplify the equation. Set it to 0, and this 2 over M. This would be the summation of I equal 1 to M of W1. And yeah, let me take one step back. No, we need to do this first. I equal, yeah, we need, which I should write it like this instead. So this will be summation of I equal 1 to M. Then I need to multiply it inside first because it contains index I. And then we have W1 xi2 plus W2 xi2 square, and then minus xi2 yi. And then I can, well, cancel 2 over M and again rearrange it into 3 terms. The first term is summation of I equal 1 to M of xi2 multiply W1. And then, oops, plus the summation of I equal 1 to M of xi2 square of W2. And then minus summation of xi2 yi, I equal 1 to M. And then again, rearrange the location so that the unknown on the left-hand side got this summation of I equal 1 to M of xi2 W1 plus summation of I equal 1 to M of xi2 square W2 equal summation of I equal 1 to m of xi2 yi. Right, so now we got two equation, two unknowns. This is equation 2. For the first equation, the unknowns are m1, w1, and w2. Second equation, we also get w1 and w2 as the unknown. So let me write it in this form using Kramer rule. So I'll get w1 equal the metric, the determinant of the summation of yi I equal 1 to m, and summation of xi to yi 1 to m. And the other terms would be summation of I equal 1 to m of xi2. And this one would be the summation of I equal 1 to m of xi2 square. Right, this is the numerator. Denominator here would be m, and summation of I equal 1 to m of xi2, right? Repeat the same thing. xi2, summation of I equal 1 to m of xi2 square. Right. Then we can multiply it down, get the result. And the first one would be summation of xi2 square. I will just write summation, all right? Summation of yi minus summation of xi, summation of xi to yi divided by m summation of xi2 square, and then minus summation of xi2 summation of xi2 square, sorry, like this. Right, and this is for W1. For W2, just do the same thing, and then you get the formula for W2. This is the method called OLS, right? Ordinary least square. By doing so, we identify the lowest point of the error curve, and then identify the parameters that should be the values at that lowest point of the error curve. And this method is used in Excel in different types of programs to learn the parameters of linear regression model. Okay. Now let me switch to the slide. So that is one of the way. Okay. Another way to view this is to use the vector calculus to define the experience, to define the learning process. So for this one, we have the MSE, the mean square error, just like what I had there, and then doing the partial derivative, right? The diff of this with respect to the weight of the mean square error. And this mean square error is 1 over m, and this is a norm, the size of the vector square between the difference between y hat and y. And because we know that for the train, this is x train multiplied by w, right? Because this is just a simple multiplying x, but we now have the capital X here to denote a lot of vector, right? To denote that there's actually a number of data that multiply, and w is just the column vector, right? Just one column vector. And because in order to solve this and multiply it, we do it. This is actually, you can see that even for this, 1 over m is cancelled out. Can multiply both sides with m and remove 1 over m. So the remaining would be the square here, and the square here is equal to having the transpose multiplied by the actual formula, right? And for this one is just like it's just like this. So this is the partial derivative, right? And we can then multiply the inside, which we got the first term x train w multiplied by x train w. We got the w transpose x train transpose x train w. If you may wonder why the arrangement looks like this is because there's transpose here. Transposition here will result in the switching between the place of the matrix, and yeah, this is the result of the first term. The second term is the this transpose, right? X w actually is w transpose and x transpose multiplied by the second term y train, right? And then also y transpose multiplied by x and w, x and w, which if you kind of pull the transposes would equal to one another. If you kind of switch location, you can have the similar value. So that's why we got this 2 of w transpose x train transpose and y train. And the last one is y transpose and y. We got this one. So think about it as y square and x. And then, yeah, it's just like normal multiplication, but although it's a little bit confusing for the matrix part. Then it comes with this partial derivative, right? The partial derivative for the first one will result in, you can think about w here as w square. So that's why we got 1 remove out, and then you get 2 here. And for this one as well, you got 2w with w here is remove it out, and we get only 2 and x train and y train. And for the last one, it doesn't contain w at all, so it is removed, right? So the remaining is like this. But once you arrange and then arrange the w to be on one side and move this onto the other side, and then multiply this term x train transpose and x train with inverse, then you get the formula of the pseudo inverse that we saw in the review at the beginning of this class, of this course. Okay, so this is the same thing as I did earlier, but on the matrix level. Okay, so once we know w here, we can calculate the parameters w based on the value of x and the value of y. Okay, linear regression will give you a line, the optimal w that pass through the data, and this would result in the best value of w that give you the lowest mean square error. Okay, so this is part of the part of the experience, the learning. Now, having linear regression, right, you can actually increase the order of linear regression. You can increase the number of parameters, or you can even increase the complexity of the model so that it becomes like the polynomial regression. But sometimes model can be overfitted, right? So the model that is underfitted, right, that is not enough, would be the model that is simple but cannot fully explain the data. The model that is appropriate would be the one that is like not that complicated, yet it can work with the data. Model that is overfitted will give you good result, well, fit with the data well, but the model will be overly complicated. And so in terms of regression, it looks like this. In terms of classification, overfittings refers to the, I would say, the learning boundaries. For the underfitting, you have the learning boundaries, the separation between class too simple, and it cannot distinguish the two classes out of one another. In the appropriate fit, you get just about right. Some might be error, but if you increase it further, the model can be overfitted and it can learn the hyperplane, the part that would separate the data into classes, to be too complicated. And once you test this with the test data, the validated data, the performance of the model will drop because the boundaries are too complicated. In terms of training the model, especially in deep learning, when you train the model more and more, right, the model will reach the stage of overfitting. In the overfitting stage, the training error will still decrease because it's trained on the training data. But the testing error, the generalization error, the error that comes from test with the test dataset will increase right after that point. You can identify it by plotting the iteration or the capacity of the model, the iteration of the model comparing to the error. All this capacity can be other thing like the number of node in the model. If you were to compare the number of node and the error that it produced, you might observe something similar to here, that even though you increase the capacity of the model complexity, the complication might not result in a better model. It might result in the worst generalization error in this case. Okay. Right. So there is this philosophy in the model that there's this called a no free lunch theorem, right? Which state that the average overall, if you were to average overall possible data generating distribution of all the generation of the distribution, every classification algorithm has the same error rate when classifying previously unobserved point. If you were to be able to take care of the all of the distribution. What does it mean? It means that we will not be able to do the above anyway. So if the model were to be able to model the distribution equally, then it would get like equal performance. So there is this trade-off between the complexity and the generalization. So the idea is to not seeking the universal learning algorithm that could be applied, but to kind of let the model learn so that it can capture the pattern and then be able to apply to another task. Okay, and that comes to the concept of regularization. We'll take a break. That takes 10 minutes break. I will come back on 7:25, and we will continue on the regularization because there will be another formula rich equation rich derivative again. So let's wait until then. So for now, let's take a break. If you have questions, put it into the chat. I will come back and answer that. Okay, let's continue. The first part, we have seen the formulation of learning from experience, learning from data. That is, you can learn parameters by identifying the lowest point in the error plane. But sometimes you want to impose other constraints into the model. Like you might want the parameters to be not that large. By imposing that, you are putting the weight decay into the weight into the error function. So that, just like this, so that you have a terms in the error function or in the loss function that would contribute to the values of the weight. In this case, if the value of the weight is large, then it will contribute to the loss. So the model would need to minimize this value to be as small as possible. And now we would have the parameters lambda here. Lambda would be the parameters that control the strength of these terms. So if lambda is 0, then it is the same thing that we did earlier. But if lambda is large, then this would push the weight to be smaller value. And we could use this to eliminate some of the parameters that might not be important. And this is called regularization. Okay. So in lambda, in large lambda, the model can be underfitted. In the medium lambda, then you get kind of appropriate weight for the decay terms, for the weight term. If lambda is 0, then the model might be overfitted. So the regularization is the ideas that you kind of contribute the significance of the weight into the loss or the error function, so that it would modify the learning algorithm. So that it would reduce the chance that the model will be overfit, and the chance that generalization error would increase, supersede the training errors. In that way, lambda is part of the hyperparameter set. The hyperparameters are in machine learnings are the parameters that cannot be learned from the model, from the algorithm. These are the values that need to be specified manually, like the lambda value, or like if we talk about like decision tree, like the depth of the trees, number of node that should be in the leaf node, for examples. In linear regressions, these hyperparameters can be the tuning of the lambda value, and that's also a hyperparameter. In polynomial regression, the degree of the model can be the hyperparameter that need to be specified. These hyperparameters can, although cannot be learned, it can be tuned by using normal data tuning procedure. This can be done by performing grid search and cross-validation to find the best parameters, like for decision tree or for random forest. We can find like number of estimator, max step, number of features that are suitable. Then we can use these parameters to fit the model, train the model again with the whole set of training set, and then use it to perform testing. Okay. So in hyperparameters tuning, the model will be replaced with different combinations of parameters, and then will be cross-validated, meaning that it would be separated into chunks, and one used for testing, and then perform training for the rest. Although these, you can see that these are quite laborious, and then it also need to have like a lot of repetitions to complete the task. This is done automatically in functions that are provided in nowadays library to use with machine learning. The estimation of the error from the cross-validation comes from the average of the fold that you specify inside here. Okay, so this is the concept of cross-validation and how to estimate error. Okay. Now let's move on to the learning of the parameters. The concept of learning of parameters often, or the process of learning itself can be defined in two styles, right? The MLE style, maximum likelihood estimation style, or the MAP, the maximum a posteriori style. And we'll see later on what are the difference between them. Okay, so if we have data points x1 to xm, from this data point we can the point estimate in terms of the statistics would be the aggregation function, certain function that take in these data points and produce estimation of values. This is the point estimate. This point estimate can be the results of the learning algorithm. This G can be the learning algorithm, take in data and produce parameters. The estimate of these parameters can contain bias. Bias is defined as bias of certain estimates is defined as the expected value of that estimated value subtract with the actual values, and then we get this the bias. So if the estimator is biased, if the measure is not biased, then the bias of estimator would be 0. That means the expected value is not different from the actual value. Okay, so in machine learning, it is a trade-off between this bias and the variations in the data. So because what? Just look at this. Bias is defined as that the value has to be close to the expected value. That means if it is close to the expected value, it's just a line, just one value, or a set of value that could define the data set. But real data contain variations. Models need to be able to account for this bias and the variance, the variation. So if we take the expected value of the difference between the mean of the estimate and the estimate itself, square, this is the variations. You can see that the mean square error is actually the square of the two, of the actual data and the result from the model. Then it could contain the variance of the model, or the errors, and the bias, which is the part that human provide. Right. The trade-off between the two will result in the different optimality of the model. Right. In the low bias, in the high bias, low variance situation. Think about it in the case of simple linear regression. You specify that you want only one parameters, one variable, right? One variable, two parameters to fit with the whole data set that contains might contains lots of variations. Then your model will be high bias, but your model will be able to take care of just a slight variance. While on the other hand, and once you increase the bias, increase the number of parameters, variance of the model will increase. That means model can take care of variance better. The bias will reduce. So as the generalization error as well, it will reduce. Right? The testing error will reduce to a certain point. After this point, the variance will still increase. The model the model can take care of the variance better and better. Right? Like it can remember each of specific page in the book, but the bias also very low. We let the model learn by itself from the data. But the problem is, doing that, the model will be overfitted to that data, and the generalization error will increase because the model would be just like remember just the book that it has without being able to generalize the concept out. So this is a trade-off between bias and variance in machine learning, and how does it relate to overfitting concepts. Now, in the estimation of parameters, there are, like I said, there are two styles of estimation: the maximum likelihood and maximum posteriorly. The first one, the maximum likelihood estimation. If we have a set of m examples, m x1 to xm, these are from independent these are drawn from the population independently, and it is belonging to the data distribution of P, right? P data X. So suppose we have this training up P of the model of X given theta. Right? This is the probability distribution with certain parameter theta. Think about this as the data, and this is like a normal distribution curve. Right? It has certain parameters, mu and sigma square, right? Mu and sigma to define that. So we are going to use this model to fit to explain the data. So this P model X given parameters maps X to the probability of its occurrence. Okay. So if the maximum likelihood of the theta that we want to estimate here would comes from the argument max of x given given theta. That means it means that the base parameters of the distribution would give the maximum probability if it put into if we put x into this into this model and theta, right? So we would get the maximum likelihood estimator. This is the maximum likelihood estimator. Get the best estimator out. Simply speaking, that the parameter should be the one that provide the high likelihood of the observations. Okay, so if we were to have multiple sample x here, then the maximum likelihood would need to be the parameter that give you the best probability given the data set like this. So think about it this way. If we have point, let's say these are the point of data. We don't know what distribution it is, but at least we collect the point of data like this out. And if we think about P model as the normal distribution, contains parameter, mu, and sigma. Okay, the maximum likelihood would be the one that results in this. This would be mu prime and sigma prime, right? And this mu prime and sigma prime will give the highest probability if you put the value of x into distribution. Because just imagine that, suppose that we were to put this x, this point into this distribution, you can see that the probability would be very low because the curve here is very, very low, right? Because the center is around here, and this would be like containing very low probability or low likelihood to multiply with. But if the distribution were to be here and we have these parameters, then you get the maximum likelihood that the model would be explanation of this data. So this is the maximum likelihood estimator, the one that gives the highest likelihood of the result. So once you know that, then we can, instead of multiplication like this, we can change this to the summation and log, because here P would be probability, it would be less than 1. So log P here would be the log of the value that is less than 1, right? That would give negative value, right? Negative values. So this should be argument min though for that case, because it's already changed to log, or it need to have something like this, minus. Yeah, log likelihood. Right, because we want the maximum likelihood. So if it were to be still be maximum, it is to be the minus of log, right? And then it will be positive value, and then we can get the highest value out. Okay, so this is the definition of the maximum likelihood. For this one, you can interpret the MLE, maximum likelihood, as to minimizing the dissimilarity between the empirical distribution, like I said, like this picture, the empirical distribution, and the hypothetical model data distribution. Right, we want to find this optimal mu prime and sigma prime. Okay, so we can For that one, we can use the KL divergence to find the difference, because we want to see a difference between two distributions. That means this is the expected value of the distribution of the data, of the actual data, minus the distribution of the model. Right? And we want to minimize this one. And we want to minimize this function, this expected value. Okay. So because this is the data distribution, that means you want to train the model. Simply speaking, you want to train the model to minimize the model fitting with X, the log likelihood of the probability that X will fit with the data, right? That X will fit with the model. And you can see the note here, the minus signs come from this. Right, the minus sign, the one that I put in earlier as well. Okay, so we need to minimize this log likelihood. So it need to fit with one another. Okay, or in other words, we need to maximize the fitting, right? Maximize the probability between the distribution of the data that the model generate and the distribution of the actual data. Okay, now because we have X alone is not enough. We have the data in both X and Y. So in that case, the theta ML has to be the argument max of this theta and X given Y, right? Because we given X predict Y. We want theta that could allow you to do that. And then this will, after conversion, it will convert this into this argument max of, sorry, I need to put minus here, minus of argument, sorry, long press here. The argument max of the minus of the log likelihood function, right, of the whole thing here, right, which is the log of P of Y given X. And let's look at the example next, that we will take a look at this in the linear regression sense. And you will see that the result would lead to the same thing actually. Okay. So in linear regression, we the model take input X and produce Y, all right? Same framework. And the mapping is the sum of square error, minimizing sum of square error. Okay. So instead of producing just Y hat, just think about earlier we draw it in a sense that the formula contains explaining each instance of X and Y, right? But instead of that, just think about it as the distribution of P of Y given X. We are now trying to find the probability distribution of Y given certain X value. Okay, the idea is to learn how to fit the distribution here, the P of Y given X, to different value of Y that compatible with X. So if we change this into the normal distribution function, because this is Py given X, this is the distribution would be normal distribution of Y, and then this will be Y hat of X and W and sigma square. What is this? This is the difference between Y and Y hat, right? Because this P of Y given X would be the center would be the difference between the prediction. Right? So that's why we have this Y minus Y hat square. Right? So instead of having X minus mu, okay, usually in normal distribution you have like X minus mu, but our mu here now is replaced with the estimator, and the estimator is the Y hat value. Okay, now Y minus Y hat square divided by the variance, the variance, and this is 1 over 2 pi standard deviation square. Okay, now from this one, we will actually solve the same thing but using the MLE notation. Okay, so now we will take log of the likelihood, log of the likelihood function or the distribution function, which is the log of this 1 over 2 pi sigma square root of 1 2 pi sigma square and e to the minus y hat over 2 sigma square here, like the exponent term, right? This is log of multiplication. Okay, log of multiplication equal log of each term plus each term, right? So this would be log of 1 over 2 pi constant value, log of 1 over sigma, and minus this term, which is eliminated because the exponential here is eliminated because we got only the exponent out here. And log of 1 over sigma is actually log of sigma. When minus sign here is actually log of sigma to the minus 1. Right? That's why we got minus here. This as well. This is log of 1 over 2 and 2 pi, right? Simple conversion. And the last part is still the same. And then making it more to be simpler term, this is constant value and m. That's why we get this m over 2 and then log 2 pi and m log sigma and minus of this whole term. Okay. Now, this is the summation of the log likelihood. Right? Summation of log likelihood. And if you remember, from this one, we need to find the lowest point. Right? Instead of framing it as some square error, now it's the summation of log of distribution. We need to find the lowest point because that would be the point that the mismatch is minimum. This is equal to the curve by theta of the log here. And just take curve by theta of the log here because theta for this one contains the sigma and would contains the value of the model, right? So by taking partial derivative of this is equal to taking partial derivative of the sum square error that we did earlier. Okay. So because they are the same, they will result in the similar instance because if you take a look at this log log of the likelihood at the end it is actually, if you think about this as constant. Think about this as constant because they doesn't contain any prediction value, and this as well because it just a constant value. Then you can see that at the end, what you have is the difference between y and y hat square. Right? That makes the two equaling to one another because the SSE sum square error is also y minus y hat square, and the log likelihood is also y minus y hat square in summation. So this would be equivalent to the other one. That means MLE is also the ordinary least square is also MLE solution of linear regression. Okay. The distribution of data must lie within the. Let me change it to pointer. So the distribution of data must lie within the family of the model, meaning that the model need to be able to, the model should represent the distribution of data. Otherwise, the estimator would not be okay. And this term actually has a lot of implication, especially if you look at the statistics book. In the statistics, when you perform linear regression, you need to verify the assumptions. Those assumptions are about the distribution of the data and the model, whether the data is normally distributed or not, because linear regression requires that the data need to be normally distributed. And we did that. We did see that earlier, that we use this normal distribution in this hypothesis. Okay. One set of parameters should correspond to one theta here, okay, so that we can use it to perform mapping between two. Otherwise, it would be like uh, if one set of data results in if one set of parameters can be correspond to different set of data, then there's no point in learning because you will always produce wrong output in that case. That is MLE, okay, maximum likelihood estimator. Another types of estimator is called, it's hard to pronounce a bit, it's called the maximum a posteriori, right? Or MAP, okay? MAP here doesn't stand for the mean average precision, right? It has been used a lot in different fields. This is the maximum a posteriori, right? Let's look at this in this sense. In order to understand MAP, we need to first look at Bayes rule. Right? In the Bayes rule, we have this posterior probability. The probability of W given D of the event W given D, this comes from the likelihood and the prior, okay, and some normalization term here. Likelihood is the likelihood that the patterns will occur in that class. Prior is the chance that that event would occur. And from Bayes rule, by multiplying the likelihood with the prior, you get the posterior probability, okay? And the MAP plays certain roles in machine learning, right? Because in this model, we can include prior, include certain constraint into the learning process, okay? So these are in the forms of basic assumptions, like in the multivariate, the mean should be 0 and variance should be constant. Okay. For the prior of the linear regression, we can have it as the distribution in exponential, and because it is multivariate, that means there are multiple variables. W minus mu minus the mean need to be multiplied to get the covariance term. In like the simpler term, this is the multiplication between W transpose and W here. In the case of this assumption that the mean are 0, right? The mean of the weight are 0. So we can eliminate the mean out and get this form. This is the prior, and from the data we have the same distribution as in MLE. This is the explanation of the distribution of data given parameters of the model. Okay, and this is the YK and minus in replacing the mean with the prediction, right? So it's X transpose and W. So it is the same thing as earlier. That means this prediction would it's the proportional of the exponential term here. Now, for PD given W, right? PD given W, and this likelihood would be the summation of all the YK, right? Because YK would be each instance. If we were to explain the whole distribution, need to take into account of every possible instances that can be generated from the distribution. So multiply them together, and this is a chance that it would happen. And this modification is proportional to the modification as well of each of the distribution when you replace the value in. That make the MAP estimation of the posterior probability. Instead of using just the fitting, using as the distribution to explain the prediction, we now have a certain prior in as well. So we would have this log of probability decomposed to the log of P of the likelihood, log of prior, and log of normalization terms. Normalization channel is usually disregarded because it doesn't mean things. One, because it's just try to normalize everything to be one. But the log of these two would play certain roles, right? Now, if we look at this, we will see that, okay, the first term here is the, if we want to minimize maximize, well, what should I say? It's actually minimize the log likelihood, because this will be a negative value, right? If you want the value to be high, you want to, if the value is close to 0, then it would be low, I should say. So it's actually maximizing it, because if it's close to 0, then it will be low. We want it to be high value. So it's max argument max of this log of P of W given D. This equal argument max of the log of P of D given W and log of P of PW, right? The first term is, think about it as data term, the data explanation. The second term is the constraint term, because it concerns only with the prior distribution. Okay, so for the first term, this term associated with the data, as I said, the difference between the prediction and the model. The second terms associate with the weight, right? With the weight, the prior probability here. Okay. So for this one, this is actually what you did in your assignment. The rich regression is actually this one. But what you did is for the rich regression for logistic regression, right? This one is for linear regression. Okay, so this would be the argument max of the error square and of the minus error square and the minus of the second terms of the weight, which give us this sum square error in linear regression, the data term, and the regularization terms that you did in the assignment. Okay, so in MAP, you can see that by imposing the prior of all the assumptions of parameters onto the model, the model now incorporate the regularization terms. So that would mean the model with regularization is the MAP estimator, right? The maximum posteriorly of the linear regression of this problem. Think about it this way. If the model contains only the SSE, it concerns only data. And that is the MLE estimator. Just take the likelihood. But if the model contains some other assumptions as constraint, then that model itself is the MAP, because it has certain assumptions that need to be incorporated, and the model need to also learn that in the error form, in the error terms, to estimate the parameter out. Right. So this is the whole framework of machine learning that you at least need to know, because proceeding further in deep learning, especially when you read the paper about deep learning, they will often mention keywords like MLE, MLP estimators, and the way to solve it by maximizing, minimizing the loss function, like that, the MLE estimator of the MLE estimator, or trying to fit distribution to one another. Okay, and what I want you to get from this lecture is that the MLE estimator is the same as the sum square error that we did earlier, right? That the simple sum square error, and the MAP is the addition of from the MLE with certain assumptions, and it makes things more complicated for sure, but it also makes model more capable in dealing with bias and variance trade-off. Okay. All right, and that is for today lectures. There are no assignments. Actually, the due date of assignment is today, but because I was sick last week, you have until next week, until the next lecture, to submit the assignment. Because the next assignment will require you to learn about the feed-forward model. So wait until then to get the next one. Okay. And for today's, I think you probably need some reviews, particularly on the latter part that contains lots of concepts in MLE and MAP. Hopefully, when you select the paper and then you read those papers, you will find that the thing that you learn in this class will at least give you some idea on what they talked about in those papers. In the especially related to machine learning, deep learning, optimization. All right. Any question that you would like to ask here? Otherwise, just give me feedback on the group. I can reply on the group as well. If you have questions when you read the papers regarding the MLE and MAP estimators, regarding the way that they optimize for the model parameters, post them into the book. I post them into the group. Once I saw, I will help as soon as much as I can there. Okay. All right. So in that case, for today, let's call a break here and see you next time. Next time we'll do some coding in building up the neural network. We'll learn the basic neural network and the feed-forward architecture. Okay. So for today, have a good night. See you next time.